So thank you for coming to listen to my talk today. Today I'll be presenting joint OH-PLIF and Mie scattering imaging of enhanced water mist suppression of buoyant fires. So my name is Xiao, and this work is conducted at the University of Sydney with the assistance of my colleagues and supervisor, so Dr. Vinny Gupta, Dr. Matthew Dunn, and Professor Asad Masri. So just to provide some context on water mist fire suppression has seen a resurgence in the past couple of years because of our increased focus on property protection. So water mist suppression systems are extremely clean, right? Because it uses pure water. They're extremely powerful because they target the gas phase. And because they target the gas phase, we can also enhance water mist suppression with inhibitor. But if water mist suppression is so good, why is it not used enough? And that's primarily because of its higher costs. There are deviations between models and experiments, and that's primarily because there's a lack of experimental data. So our primary objective is to essentially try to push the database in terms of water mist fire suppression such that in the future there are better attempts at model validation. So the first thing we do is essentially design a canonical laboratory scale experiment. We'll characterize the boundary conditions using PEI to obtain all our droplet statistics. We can then enhance our suppression capabilities with inhibitor, so in this case, alkali metal salts. We'll create maps of flame extinction to look at how increasing concentrations of alkali salts changes the behavior of flame suppression, and then we'll perform some simultaneous high-speed Mie OH-PLIF imaging. So let me first go through the experimental setup. So our experimental setup is essentially a co-flow design. So what we mean by that is we have our burner sitting in the middle of the wind tunnel, and recessed in the wind tunnel is a nozzle holder which holds, in our case, up to 6 water misting nozzles. So our fuel in this case is 36.6 standard liters a minute of CNG, so compressed natural gas, which is effectively a 20 kilowatt flame. Our burner diameter is 35 millimeters, wind tunnel exit plane 250 millimeters by 250 millimeters, and we use 6 red type KBN hollow cone misting nozzles. So these nozzles produce water mist with a cone angle of about 80 degrees and a nominal droplet diameter of 50 microns. And on the right is just a video of what this experiment looks like. Okay, so to characterize the exoplane boundary conditions, we use phase Doppler interferometry. So we use a RDM PDI 300 system, which gives us point measurements of droplet diameter distributions at the exoplane. This is a 3-component system, so this measures 3-component velocity, x, y, z. And what we do is essentially we traverse the entire exoplane, so in x and y, to obtain droplet statistics at every single point. So with our PDI measurements, we essentially do a measurement of the entire exoplane at a given flow rate of water. So our exoplane is discretized into grids of 1 centimeter by 1 centimeter, and we perform a measurement at each of these grids. And at each of these points, we take approximately 60 seconds of data for 3 components of velocity, diameter distributions, and volume flux. So on the top left, we have a graph of velocity. So essentially, velocity peaks at around 0.9 meters per second near the burner, which is in the center, and drops off to 0 near the edges of the wind tunnel. So volume flux follows a similar profile to velocity, just more asymmetric because of your manufacturing differences in each of the nozzles. And down at the bottom we have measurements of droplet distributions, D10 and D32. So D10, you can see it's quite uniform around 20 microns, and D32 is also quite uniform around 50 to 55 microns. So previously I showed you a measurement at a constant flow rate of water mist, but we're operating this experiment at a wide range of flow rates. So what we do is essentially do that exoplane measurement at a low flow rate, at a high flow rate, and a medium flow rate. And with these 3 flow rates, we can essentially construct a calibration curve to fit all our data to the varying flow rates we use. But one one thing we have to consider as well is because this is a co-flow configuration, our input flow rate will not equal our output flow rate, right? And the reason being is because you get water deposits on the inside of the wind tunnel, which prevent water mist from actually leaving the wind tunnel. And because we did exoplane measurements of volume flux, we can actually integrate the volume flux along the entire exoplane to obtain an effective volume flow rate. And that is what we have done here. So with our PDI measurements at the 3 flow rates denoted by this black circle, we can convert our input flow rate, which is known, to an exoplane flow rate, which is unknown. And this is essentially the 3 data points we have for absolute exoplane flow rate of water mist. And to validate this data, we essentially place a water tank inside the wind tunnel, and by virtue of conservation of mass, so the difference between your input flow rate minus the amount of water collected in the wind tunnel will effectively give you the total flow rate of water leaving the wind tunnel. And that is plotted as the blue triangles on the graph, and you can see whether or not it's with measurement by PDI, so integrating the volume flux measured, or by conservation of mass through a collection tank. Both results converge quite nicely and give us a calibration curve to convert input nozzle flow rate to absolute exoplane flow rate. And on the left is essentially a cross-section of those profiles we took for the 3 different flow rates. You can see at D10, the droplet diameters are around 15 to 20 microns, quite uniform. D32 is quite uniform, around 45 to 50 microns. And the volume flux increases in a parabolic profile with increasing flow rate, and velocity increases in a parabolic profile with increasing flow rate. So now we'll briefly look at the inhibition mechanism of enhanced suppression. So water mist we know targets the gas phase. So what this means is droplets evaporate near or in the flame front. And if you include inhibitors such as sodium bicarbonate in this case, what happens is, if you look at the diagram on the right, these droplets, as they come out of the co-flow, as they get closer to the flame front, the droplets get smaller due to evaporation, and once they fully evaporate, they release sodium crystals, or sodium bicarbonate crystals, and these crystals, at given temperatures, thermally decompose into your inhibitor, which is sodium hydroxide. So the general process follows this. At around 400 Kelvin, sodium bicarbonate decomposes into your sodium carbonates. At higher temperatures, 900 Kelvin, your sodium carbonates thermally decompose into sodium oxide. And then at really high temperatures, so reaction near the reaction zone, your sodium oxide decomposes into sodium hydroxide. And sodium hydroxide is the catalyst that recombines these intermediary combustion radicals into a stable molecule. So in this case, sodium hydroxide combines with the free hydrogens to form atomic sodium and water. And atomic sodium forms with your hydroxyl radicals in the flame to reform sodium hydroxide. And this process, catalytic process, effectively converts your hydroxyl radical and your free hydrogens into water. Alright, so here is just some example videos of inhibition. So on the left we have our turbulent buoyant diffusion flame. The second video, pure water mist, you see a big reduction in flame luminosity. With sodium bicarbonate you effectively get a bright orange flame, and with potassium bicarbonate you get a pale blue purple flame. And what is quite interesting from these videos is if you look at the potassium bicarbonate specifically, you can see these large sort of extinction holes forming in the flame front. Alright, so now let's look at flame extinction. So extinction in our case is defined by the video on the left. So essentially when the time it takes for the flame to go from stable anchored to lifted, that delay time we will call extinction delay time. And the graph on the right shows that extinction delay time with the varying flow rates of water mist. And what we can see is that this extinction delay time follows an exponential curve, whereby if you decrease the flow rate, the extinction delay time exponentially increases to effectively infinity. And what happens if we add water mist? Inhibitor in the water mist. We can see that the curves essentially translate to the left but maintain the same profile. What if we add more salt in the water mist? and more salt in the water mist. So what we see is with increasing alkali salt concentration, whether it be potassium bicarbonate or sodium bicarbonate, these curves essentially translate to the left. And what we found was every single one of these curves follow the exact same profile, which is defined by the relationship in the bottom left, which is your extinction delay time is proportional to the inversely proportional to the flow rate of water minus a constant, which is the flow rate at which you achieve an infinite extinction delay time. So with that relationship we found on the previous slide, we can convert our extinction delay time and flow rate space into a flow rate versus inhibitor concentration space. So for example, if you look on the graph on the left, it's a potassium bicarbonate stability map, which shows essentially the flow rate requirements to achieve extinction with different concentrations of potassium bicarbonate in the water. And what we see is essentially with increasing concentration of potassium bicarbonate, you get a steady decay in the flow rate requirements required to achieve flame extinction or flame inhibition. We have the same thing for sodium bicarbonate here in the middle, and we can see from these two graphs that potassium bicarbonate is significantly better than sodium bicarbonate at inhibition. And just to note as well, this concentration on the x-axis is essentially how much of the inhibitor we can physically put inside water, right? Because they have saturation limits, and to keep the comparison sort of true and meaningful, we've also included concentration by moles per liter and a graph on the right comparing grams per liter as well. And even with grams per liter, we can see potassium bicarbonate is significantly better than sodium bicarbonate. So now we have the stability maps done, let's do some high-speed imaging. We really want to figure out where these droplets sit with respect to the reaction zone. So we do a simultaneous high-speed imaging of OH-PLIF and Mie scattering of droplets, where we excite the OH to approximate the reaction layers, and Mie scattering for droplet position. We image at a rate of 400 Hz, and our image window is around 55 millimeters, and we image a total of 0 millimeters to 240 millimeters. Okay, so now let's look at some of the droplet Mie scattering images we took. The image on the left just shows our measurement region relative to the flame. So if we look at the set of videos here on the left that's playing right now, so this is of pure water. Essentially the orange color map is the OH or the reaction zone, and the blue color map is your Mie scattering of droplets. And what is quite interesting is that the flame is quite continuous down the entire length of the flame. Your droplets permeate the air side and barely penetrate into the fuel side. You can see some breakages downstream of the flame, which are local extinction zones. Now with sodium bicarbonate, you get more of these breakages forming in the flame front, especially further downstream, and that is caused by the chemical scavenging of your OH radical. Now this is even more significant with potassium bicarbonate as seen on the right, where you get extremely large extinction zones in the flame front, and in some frames you have no flame at all. So now let's look at just some OH statistics we obtained. So this is just comparing max OH counts versus axial distance of the flame, and this is for water only, sodium bicarbonate, potassium bicarbonate at different blow-off percentages. So blow-off is just a flow rate percentage of the infinite extinction delay time. Alright, so higher blow-off means you're in the unstable regime, a lower blow-off means you're in the stable regime. And what's quite interesting is with increasing blow-off percentages, your OH monotonically decreases, and with different inhibitors, so from water to sodium to potassium, your max OH counts decreases even further. So just in summary, we've designed a Mie suppression experiment. We've characterized its boundary conditions, looked at flame suppression stability maps of different inhibitors at different concentrations, and performed a simultaneous high-speed OH-PLIF and Mie scattering of droplets. Now we really want to extend that high-speed imaging data to obtain some sort of droplet evaporation statistic, or how these droplets cause these extinction zones in the flame front. So as an extension of the previous work which I've shown you, we will further extend our experiments to look at simultaneous OH-PLIF for the reaction zone and 4D PTV. So we'll look at obtaining Lagrangian particle tracking of every single droplet we can see in the flame. And this is done with essentially this experimental setup here. So here are some of our preliminary results. On the left, you can see essentially high time resolution of how droplets cause these extinction holes. And we have on the right examples of 3D particle tracking. So these are droplet trajectories in 3D space. And this is performed through a technique called tomographic reconstruction, where we can get some form of droplet evaporation statistics. Yeah, thank you for listening.